In this video, we're going to talk about function notation, and we're kind of introducing functions for the first time. And what we'll do is we'll kind of build on some ideas that we already know to help us bridge to what a function is. So suppose I wanted to graph y equals x cubed. And at the end of the last chapter, we talked about when you're graphing something for the first time, it's wise to go ahead and plug in some points. So I'm going to make a little XY table over here, and I'm going to plug in 0, 1, 2, -1, -2. So those are the starting points I like to plug in for the first time for something. So when I plug in 0 for X, that's going to give me 0 for Y. And I'm not going to show the work on that. I think most of us see that when you plug in 0, 0 cubed is going to be 0. When you plug in 1, 1 cubed is going to be 1. When I plug in 2 cubed, that's going to come out to 8, because 2 times 2 times 2, that's 8. -1 cubed, that's going to come out to -1, right? Because you'll multiply -1 by -1, which is +1, but +1 times -1 comes out to -1. All right, and then -2 cubed will be -8. So similar to what 2 cubed is, except because it's negative, it will come out negative since there's an odd number of negatives. All right, so I'm going to go ahead and plot this. And I'm just going to kind of do a few tick marks. I'm not going to go crazy since I'm drawing this. Okay, so 1, 2, 3, 4, 5, 6, 7, 8. And I'll have to extend down here, I think. 1, 2, 3, 4, 5, 6, 7, -8. Okay, so plotting 0, 0, 1, 1, 2, 8, -1. I'm sorry. Yeah, -1, -1, and then -2, -8. Okay, so here's what it looks like. Kind of looks similar to a parabola, except instead of reflecting upwards, it kind of goes downward. Here, I'm actually going to fix the fact that it's not going through that dot. Boom. I don't know if that's all that much better, but there you go. Okay, so it kind of looks like this. Now, I wanted to kind of use this as a starting point because I wanted us to consider the steps we took. So first thing I did was I decided on values I wanted to plug in for X. That was the first thing I decided to do. And those values, we typically call those inputs because I'm choosing them first and then I'm inputting them into this equation right here. And that would mean then that the values we get for Y are outputs because they're based on all of our X values. And that's the kind of building idea behind a function. So let's look at the definition. Functions have at most one output for any input. So X is generally the variable we plug in. Y is the variable we evaluate. X is considered to be the input. Y is considered to be the output. So the definition is for any, here, so I want to kind of emphasize this is the part we're focusing in on. For any X value, there is at most one Y value that corresponds to it. And this word, or I should say phrase, at most one, implies that beyond one, we have a problem. Now, we'll talk about that in a little bit more detail when we discuss what makes something a function. Before we do that, I want to note that we have a different phrase that we sometimes use for input and output. So we often call input the domain and output the range. So input and output is kind of an easier idea. We have a little bit of understanding based on stuff we've done with equations before. So let's build on that, and then we'll come back to the definition of a function. So looking at this example, we want to know what the domain is for the following. So we already looked at y equals x cubed, and what we're really asking is what type of inputs can we plug in for x? So when I come back up here and I consider then what values I plugged in for x, the question kind of becomes, what other values could I have plugged in? I didn't have to do 0, 1, 2, -1, -2. I mean, I could have done 100. I could have done 1/2. I could have done 0.72. I could have done anything I wanted to. And I could grab my calculator and figure out when I cube it what I get. And because there's no limit to what I'm allowed to plug in, that means then that the domain is all real numbers. I can plug in anything I want. I'm not limited. That will not always be the case. So let's look at the next example. Here, we have a rational equation. And in this case, we actually have a potential problem. The problem we can have is that we are not allowed to have 0 in the denominator. We've talked about that before. So because I'm not allowed to have 0 in the denominator, I can plug anything else except whatever value I plug in for x that gives me 0, that's a problem. So I can plug in 6, I can plug in 0 for x, but the one thing I can't plug in is 7. So x just can't be 7 because 7 is going to give me 0 in the denominator. And if I wanted to write it out as like a little equation, this is how it would work. I'd set the denominator equal to 0, solve for x, and that is the value x can't be. Now, because it's kind of a simple equation, it wasn't hard to figure out by just looking at it, but that's kind of the process we might take if we're not sure by just looking at it. You'd set the denominator equal to 0 and solve for x, and that would be the value that it cannot be because it would give you 0 in the denominator. Okay, so another one that we might have a potential issue with is like the square root. We can't have negatives in the square root. So what I'm going to do is figure out when this thing equals 0. And what I'd like it to do is to be bigger than or equal to 0. So I'm using an inequality. So I'm saying as long as it's bigger than or equal to 0, I'm good to go. So I'll solve this just like any equation. Having the inequality there is not a problem. We just have to flip the sign if we divide by a negative, which I'm not going to. So I'm getting that as long as x is bigger than or equal to 2/3, we won't get a negative in the domain. So there it is, that's the domain. X is bigger than or equal to 2/3. Okay, so let's emphasize this a little differently. What if we were looking at a cube root? Now I'm wondering, do I have to worry about having negative numbers in a cube root? And the answer is no, because remember, we can actually find the cube root of a negative number, like -8. The cube root of -8 is -2, because if you cube -2 times -2 times -2, you get -8. So with a cube root, we don't have to worry about negative numbers. And therefore, I'm not concerned about the same restrictions. In fact, I can plug in anything I want, kind of like the very first one we did. So this one is a domain of all real numbers. The cube root makes all the difference. We're allowed to plug or have negatives under a cube root. So anything with an odd root, we're okay. Anything with an even root, we have to have it bigger than or equal to 0. Okay, so the next one here, we have another fraction. So I have to worry about the denominator equaling 0. So I'm going to make it equal 0. And I'll go ahead and solve it using the square root. So I'll get the x squared, take the square root of both sides. So that's going to be plus or minus 5. So in this case, we don't want it to be plus or minus 5 because that's going to give us 0 in the denominator. So it can't be 5 or -5. And I can list it with a plus or minus, but you may have to list it out separately in MOM. Okay, so now let's come back to the definition of a function. So remember the thing I underlined. For any x value, there is at most one y value that corresponds with it. Okay, so let's look at this first example here. For all of my x values, so I'm zeroing in on the x's. So I have x goes from 1 to 3, 0 to 1, 3 to 2, 2 to 1. All of the x values, they're all unique and they all go to a different y value. Now I see that in the second one and the last one, they both go to the same y value, but that's okay. We're allowed to have x values go to the same y value. What we can't have is an x value that's paired up with more than one y value. So this is a function. This next one, however, is not. And the reason is the fours, the fact that this 4, this has a 4 and this has a 4. So that x value of 4 went to 2 different y values. It went to 1 and it went to 3, and that's a problem. So it can't have more than one y value. It can only have one y value. So this is not a function. So we're focusing in and making sure that the x values are only going to one y value. I'm not worried about repeating y values. Okay, that's okay. It's repeating x values that are a problem when I'm looking at this. Okay, let's apply that to a picture. So the idea is all of the x values are being represented here on the x-axis, and the y values are the outputs for each of these x's, right? So for this x right here, there's its output right there, right? And for this x right here, there's its output right there, okay? And the idea is every x value here goes to only one y value. So this x value that's right here, that goes to this y value. And this x value that's right here, that goes to this y value. They go to the same y value, but that's not a problem. It's a problem if an x value goes to 2 different y values. So this one's a function. But the next example, sorry, that was kind of weird looking. Let me fix that. Is not, because like, let's look at where x equals -2 here. Okay, at -2, there's a y value, but it also goes to another y value. So that -2 is being paired with 2 separate y values. That makes it not a function. Now, here's what's kind of nice. There's actually a really easy visual way of checking if a graph is a function, and it's called the vertical line test. So if we draw a vertical line and it hits the graph more than once, it's not a function. So if you draw any vertical line and it crosses the graph more than once, then it isn't a function. So on this first graph, anywhere I draw a vertical line, it's only going to cross the graph once. But on this second function, it crosses the graph twice in a bunch of different places. It only needs to happen in one place for it to not be a function, okay? But if you draw a vertical line and it crosses more than once, not a function. And actually, if you think about our previous example with the ordered pairs, and you were to plot out these ordered pairs, this one would fail the vertical line test, because at the point where x equals 4, it is at 1 and 3, and that would fail the vertical line test if I were to draw a vertical line. So the vertical line test is a way for us to visually check whether or not something is a function. Okay, so let's say we have this, and I'm kind of like, okay, is it a function? Now I could draw it, I could graph it, and there'd be nothing wrong with that. But I could actually tell that if I plug in any x value at all, anything for x, like a 1, I'm only going to get one y out, right? So if I plug in x equals 1, for instance, I'm going to get out y equals 3. I'm not going to all of a sudden get y equals 3 and 4. It's only going to come out y equals 3 when I plug in 1. So for every input, there's one output. That makes this a function. But looking down here at this one, let's say I plug in 1 for x. If I plug in 1 for x, then I have to solve this little equation. And I'm going to take the square root of both sides, which means I get plus or minus 1. Ah, that's a problem. We can't be plus or minus 1. That's two y values. I plugged in an x and I got out two y's. That's not a function. So I'm just making sure that for every x value I plug in, I'm only getting out one y. And it'll be relatively obvious like this, where I end up taking a square root and I get a plus or minus. Okay, that's not going to work any longer. But I could, if I wanted to, I could graph these, maybe go to a website that has a graphing calculator like desmos.com. That's a website that has a graphing calculator. And I could graph these and I'll see if they pass the vertical line test. So that's kind of a backup way of checking whether or not something is a function. But really, I could just kind of plug something in and see that I'm going to get out two y values on the second one, but I'm never going to get out two y values on the first one.